curve en suffisant, il y aura un des descentes, il est clair, il ne peut pas avoir
D'accord. Parce qu'il y a un exemple là, celui-là, on est sûr qu'il est tombé dans le cul parce que c'est dans l'orbite, mais c'est pas sûr.
J'ai pas besoin de temps.
Maybe let's start so we can have a longer break. The second talk in the afternoon is by Hugo, so we'll continue with the lecture.
Thank you very much. So, right, so the goal of this hour here is to prove the theorem of Jeff Brock that says that the Pants graph is a combinatorial object that describes the Bay-Peterson geometry of Teichmüller space. Precisely that the two as metric spaces are quasi-isometric. Okay, so we've looked at, or I've defined this Bay-Peterson distance on Teichmüller space. And I'm just going to list some properties that are, this will just be a black box about these properties. And let's just keep these in mind. So it's a Riemannian metric, okay, but it's not complete. Result is true. And the reason, and the quantified version of this non-completeness is the following, which is due to Wolpert. And that is called the length of pinching rings. And visually, this is what happens. So, if you're on a surface, take a multi-curve, a geodesic multi-curve, and the length of this multi-curve on this surface is equal to L. Okay, so this surface here lies in the Teichmüller space. This is S. Okay, so this is a result of Wolpert that says that you can go. You can find a path, that this path here lies in Teichmüller space, and you can get to a surface. So now I've gotten myself into a, okay, so I have to draw something. There we go. Okay. You can go in Teichmüller space. You can pinch these curves down, like this, until they actually reach 0. Okay, so this, of course, no longer lies in Teichmüller space. Okay, but this is the limit of what you get. And the length of this ray here, okay, the length of this path, is bounded by an explicit function, the function of n. In fact, it's less than the root of 2 pi times that L. Okay, this is true for any multi-curve. So the length of the multicurve is the sums of the lengths. Okay, and this is a result of Wolper. Okay, so you can pinch multicurves. Pinch to 0 in the root of 2 pi times the length of the multicurve. Okay, but in fact, yeah?
The limit is obtained by shrinking the multicurve, or what?
Exactly. Yeah. I mean, there's a continuous path. So there's a continuous path that goes from here, and the multicurve gets smaller and smaller. And so as long as this multicurve actually has some length, you're still in Teichmüller space. Okay, but then in finite time, you've arrived at a degenerate surface. Okay, and in fact, that's the only way you can degenerate. Okay, that's the only thing that can happen. Okay, so in fact, the metric completion is, well, actually, yeah. Okay, so this is not entirely proper what I'm writing. Okay, this is the Lin-Mumford compactification of Teichmüller space. It's a result of Parlier. So what I mean by this is that this is the only thing that can happen. Okay, this is the only thing where you actually get incomplete geodesics. This is the only thing that happens. Okay, and so what you do is you get this here by adding strata. Okay, this is equal to this union strata. What strata are copies of lower dimensional Teichmüller spaces obtained by pinching multicurves. Okay, so for each multicurve, each element of the curve complex, if you like, you look at surfaces that have that curve, the length of these curves equal to 0. Okay, so what you get is noded surfaces. Okay, so an example, you have a genus 2 surface. Okay, so one possible way is that you're going to add a stratum corresponding to this. Okay, so you pinch down this. This is a stratum that you're adding on, but you're also going to add down a stratum that corresponds to something more extreme. Okay, where you've pinched all of these guys. Okay, so you add on this stratum. This is only a point. Teichmüller space of this is only a point. And you add on everything that's possible. And you do this for every element of the curve complex. Does that make sense? Okay, so you get this metric completion. Okay. And what happens is
So I don't understand, sorry, Hugo.
yeah.
So this is a sequence, so this is not complete because you
Because
show
you can do this in finite
a
time.
sequence which is a Cauchy sequence, which does not.
Right.
How about in the Teichmüller metric? This is not.
This doesn't happen. So in the Teichmüller metric, it takes you an infinite amount of time to go to a pinched surface. So geodesically complete. So you can always complete in the Teichmüller metric if you go from one point to another point. Okay, you look at a
But
geodesic.
while this same example does not show that Teichmüller metric is not complete?
Because it's infinite. This surface here is infinitely far away from this surface here. And the reason that it's infinitely far away is because the Teichmüller metric, what you're recording is local deformations. So in particular, the ratio of curves, for instance, if the ratio explodes, then that's an impediment to being able to get there in finite time. Okay. And so you get this metric structure at the limit, okay, this metric completion, and what happens to the metric on this stratum here? Okay, and this is you get a product metric. On the stratum. Okay, so what does this mean? This means that if you have mu such that a surface, our topological surface minus mu, is a disjoint union of surfaces. Okay? Then the metric that you get on the stratum corresponding to mu is exactly the product metric of these. This is the metric on the stratum defined by mu. So you can, each stratum is parameterized by this mu. So I'm going to call this, I don't know what I'm going to call it. What do I call this? Okay, something like that is the product of these guys. Okay, so for instance, the metric that I get on this stratum is exactly the product metric that I get on the two lower Teichmüller spaces of these. Okay, so to compute distance in here, I look at the distance in here and I just look at the product metric between the two. And here's another result that's sort of important, that's important for what I'm going to do. This is sort of the last thing, is that these, within this metric space, now I get a complete metric space. Within these metric spaces, the strata are completely geodesic. Strata are, well, I'm going to write this down like this, but convex. This is a result of the Okay, so in this new metric space, if I now have two surfaces that are degenerate along this, that lie in the same stratum, any geodesic between them will remain entirely in this stratum. Okay, I have no interest if I give you give me two different two different degenerate surfaces of genus 2 that have been pinched along the same curve. Any geodesic in this metric space will always cube that degeneration.
So this metric is going to have negative curvature?
It's actually a cat 0 metric space. So not negative, but it's cat 0. So there's lots of other properties that I'm not going to mention here. I'm just going to say that sort of in terms of comparison, Bay-Peterson and the Pants graph, okay, they both have the mapping class group as isometry group. Okay, so they both have the mapping class group. This is a theorem of this, depending on, so this one here, for this one it's Margaret. And this one here, it's essentially a theorem of Maser and Wolf. then some exceptional cases that were computed by Brock and Marble that were left over. Okay. And the theorem I want to say is that these two are actually have a much closer relationship than that. The theorem of Jeff Brock. Okay, that Teichmüller space here. I can look at the completion. The metric completion is quasi-isomorphic. Let me just write this down. And with the usual distance. Okay, are quasi-isometric. Okay, so this is, I mean, it's the same thing as saying that the Teichmüller space itself is quasi-isometric to this, because it's quasi-isometric to its metric completion. But, okay, so let me, I assume most people have seen this before, but let me just recall, and that way I can sort of fixed notation of what this actually means. So if I have a map F from one metric space to another metric space, okay, is, you say it's a quasi-isometric embedding. The following is true. So if I look at the distance in the image, okay, so I look at y1 and y2. Constants, A and B, such that for all y1, y2 that lie in my domain, the distance between what I get here is going to be bounded by A times the distance that I originally had in y, between y1 and y2. Plus a constant. Okay, so it's Lipschitz with an additive constant. And the same thing is true on the other side. So I get 1 over A times the distance here in y, between y1 and y2, minus the same constant b, so I get the same inequality. And if the image of the domain is R dense. Okay, so every point in X is R away from some element of the image of Y. Okay, so R is a finite constant. Then F is a quasi-isometric. And in particular, I mean, so this is the definition of being quasi-isometric, the existence of such a map. Okay, before going on, I want to make another remark that one of the things that this relies on, which I won't get into, is the following theorem of Ferris. Says the following, that there exists a constant okay, which only depends on the sigma, so the topology of the surface, such that any S that belongs to the Teichmüller space of this has a Pants decomposition of length at most this constant. Okay, it's some constant, only depends on the topology. Okay, so it turns out I have a lot to say about this theorem, which I'm not going to say. Okay, but if anybody wants to ask me more about this theorem, in particular how you quantify these constants, I'm more than happy to spend 3 or 4 weeks with you in the Bahamas explaining it.
So maybe before you continue, I have a very naive question. So what's the motivation for this result abroad? Why did you do this?
Oh, so why do you want to do this?
Yes.
Well, that's a good question. So this is somewhat difficult. It depends what you want to do, but this is somewhat difficult to, as an object, to know what's going on. I mean, it's a technical definition of the distance to begin with. How you actually compute distances between surfaces is not clear. As an example, I don't think there's any known example of 2 surfaces where we actually know their Peterson distance.
Yes.
Okay, besides the fact, yeah, so that's an example. Okay, so nothing is known in that aspect. So this is a combinatorial object. Okay, so it's easy. Okay, so in particular, using this has allowed us to say things about this, and has allowed Jeff did a lot of things about hyperbolic free manifolds.
Oh, I see.
Okay, and was only able to do that because he had this association.
Okay.
Okay, so I mean, there are many applications of this.
So what kind of result for is it a 3-dimensional hyperbolic manifold?
Yeah. So about volumes, for instance. Because, anyways, but that's a whole other sort of. But in general, I mean, think combinatorial, hands-on object. You can compute distances. On the other hand, something more difficult to handle. So, but here's the proof. So, okay, so first of all, what's the embedding? And the embedding is exactly what you might expect. Okay, so you take F, it's going to go from the Pants complex to Teichmüller space. Okay, the completion. And you take P. Okay, you take a maximally embedded, you take a maximal multi-curve. Okay, and you send it to the unique surface in there with the length of P equal to 0. Okay, does that? Let me show you a very concrete example. So the surface you send it to is just a collection of 3 punctured spheres, okay, with a hyperbolic metric that is glued together in some way. So, for instance, the example I just keep drawing over and over again, but okay, so here's the example, and I send it corresponding to this. Okay, this is an element of P sigma, okay, and then I send this to exactly this one. Okay, there's only a unique conformal structure that this corresponds to. Okay, and I do this for every single Pants decomposition. Okay, this defines a map. Okay, so the first observation is that the length of pinching rays, this thing by Wolfert, plus the theorem of Beers, tells you that every point in Teichmüller space is some bounded distance away from one of these. Okay, so the Beer's theorem plus the length of pinching radius implies that the image, this, is R dense. Okay, for some R that depends on the Beer's constant. Okay. R you can take equal to the square root of 2 pi times the Beer's constant. Exactly. Okay, so what I need to prove is the two inequalities.
So here actually we can also define an inverse map. Just take a bad tens basically.
Interesting.
You want to define inverse map from the Teichmüller space to the bands complex. Right, you start with the hyperbolic surface.
Sure.
Take the bands.
Oh, absolutely. Yeah, sure. Absolutely, yeah. That's exactly what I'm going to do.
Oh.
But yeah. Okay. But the first thing you want to do is you want to show that your image. I mean, in fact, well, this avoids some of that. But I mean, you do have to do something like that. Okay. And what this does here is that sort of step one is to show that the distance in Teichmüller space, okay, between the f of I'm going to say p and f of q. So for all p and q, Pan's decompositions, I want to show that this is bounded by some a times the distance in the Pan's graph times pq plus b. Okay, so how do I do this? Well, okay, so I have something that looks like this locally. Okay, a local picture. And what I want to do is I want to find a way of emulating in Teichmüller space these elementary moves. Okay, so I want to go to something that looks like this. I have some theoretical curve. Yeah. So what I want to do is this. I want to move from here to something where it looks like this. Okay, so this is my original blue curve. This is some red curve that's degenerate, and I want to move to something like this. Okay? And then I want to take this, and then I want to go to replacing the blue curve with the red curve, so this turns out to be. So this is easy. Why? Because I look at this. Okay, so to get from here to here, well, I don't know what this distance is. Okay, but it's certainly the same distance as to get from here to here. Okay. And I can find a surface here where these two lengths aren't too long. Okay. I can actually find a surface, I can actually tell you what the lengths could possibly be. Okay, you can construct a hyperbolic surface like this, where these two lengths are actually going to be 4 times arc sinh of 1, but it doesn't matter. Okay, they're both of a certain length. Okay, and to get from here to here, all I need to do is pinch along this. Now I know through all these convexity properties what the Weil-Petersson metric looks like. If I'm letting the whole rest of the surface be as it is, it's some maximally pinched things, and I know that all I'm doing is changing in this particular stratum here. Okay, so I can compute the distance between those two. Okay, so this only costs a constant. This only costs, at most 10 to the power of 10. Okay, that's much too much. It costs 10 is enough. Okay, but I'm just saying it only costs a constant. So I can emulate elementary moves in Teichmüller space. Okay, so in particular, this tells me that to get from this surface here to this surface here, all I have to know is if I know the combinatorics, if I get from one Pan's decomposition to another, each time I make a move, I can replace it with this. Okay, so I'm going to call this some constant C. Okay, and then this tells me that the distance here between f of p and f of q in Teichmüller space is less or equal to my combinatorial distance between p and q times this constant c. Okay, so that's, I'm done. That aspect is done. Now the second step is more difficult, but I mean, morally it's sort of the same thing, but it is more difficult.
Does this map F behave well under the action of mapping Casimir?
Yeah, because you can.
It seems, yeah.
Yeah, sure. Yeah. It's this one is this one's a real map. I mean, it's a real honest to goodness map, and but the opposite is that everything is sort of quasi on the other end. Okay, so what Lishen was hinting at is one thing I can do is I can take all of Teichmüller space. So step 2 is the other way. So I want to get the distance in the Pants graph. Okay, and I want this to be bounded by some constant times the distance in Teichmüller space less than constant. Okay, so the idea here is now I take some f of p, and I look at some f of q, now I'm in Teichmüller space, and I want to be able to compare the distance between p and q in function of this. Okay, so what I can do is I take an actual geodesic in the Peterson space, and I can sort of separate it into little pieces. Okay, and each piece here is of length, 1. Okay, so each one is of length. Each one of my little segments is of length 1. Okay, so what I can do is I can now cover Teichmüller space by balls or by sets. They're not balls, but I don't want to. By sets VL, okay, which by definition are sets where X, if X admits, so, sorry, I actually indexed this by P. Okay, so P is a Pants decomposition, where the length on X of P is less or equal to L. Okay, so Bers's theorem tells me that there is some L for which this covers completely Teichmüller space. Okay, every surface has a Pants decomposition of length at most the Beres constant. Okay, so I take L greater than the Beres constant, and then these cover Teichmüller space. Okay, and the fact that these cover Teichmüller space means that, in particular, every one of these segments is covered. By one of these sets. Okay. These are BL sets. So now there's sort of, you need to say something about the geometry of V. Peterson to be able to complete the argument. Okay, you need to do something about, essentially what you need to know is that when you go along this, okay, so morally what's happening, you're going along this, you're changing sets VL as you go along. So to each set VL, there's a Pants decomposition, so this defines a quasi-map into the Pants graph. Okay, so why is this a quasi-map? It's a quasi-map for a very simple reason, is that if your L is sufficiently big, your surface can have many Pants decompositions of length less than a certain constant. Okay. So that is something of a problem, right, that you have to be able to handle. Okay. And you also need the fact that if you go from one of these sets to another set, that the two Pants decompositions that are related aren't too far apart. Okay, so this is really the technical aspect of the proof, which boils down to two pretty simple lemmas. Okay, and let me just write down the lemmas. So the first one is that there exists a constant. KL, such that any geodesic segment of length 1 is covered by KL sets of type BL. So first of all, each one of these segments I can cover by a finite number of these sets. Okay. So this already, I'm starting off by sending this segment to a finite number of Pants decompositions, which is already good. And it's a universal finite. It doesn't depend on where I was to begin with. Okay? So that's a good thing. And the second good thing that happens is that there exists another constant, K tilde L, such that if VL P prime and VL P double prime intersect, then their Pants decompositions are combinatorially close. And the distance in the Pants graph between these two, okay, is bounded by this constant. All right. So once I have this, then I'm home free. Okay. Because then what I can do is say that the distance in the Pants graph between my original P and Q, okay, is bounded by, well, the number of segments I have between the two is exactly, I mean, or more or less the length, the distance I originally had. So this is the distance in Teichmüller space between f of P and f of Q. The number of segments I have to multiply times these two constants, so I get KL and K tilde times L. And then I'm going to add something, just, I mean, a big constant in the beginning, I guess, something like this. Well, I mean, just some other big K. Because I have to watch out for, I mean, the number of segments I have is fine, but then at the end I might have a 0.3 that's left over or something like that. Okay, so I do need an additive constant for this. Okay, this is just for the leftovers. Okay, and so that's the proof of Justin.
So this part from FP to FQ,
Yeah.
is not containing the image of F, right? Doesn't
No, because F has image just points.
it's not connected, right?
Exactly.
The image
Yeah,
is not connected.
yeah.
Okay.
Yeah.
Okay.
Yeah, this path is in. This is a geodesic path.
Inside technical space.
Exactly. And in fact, it's for the reasons of convexity that I was saying. Besides in its terminal points, it actually lies entirely in the open part of Teichmüller space. I mean, if the two Pants decompositions are completely different. Okay. If they both have curves in common, then it's going to stay in that strata. Otherwise, it goes straight into the open part of Teichmüller. So what you get is a corollary of this. Pants graph as an object, as a geometric object, is not normal hyperbolic. Okay, and why is that? Well, let me tell you why the Weil-Petersen metric is not Gromov hyperbolic. Okay, so the obstruction to being Gromov hyperbolic is that you have flats or quasi-flats into space. So quasi-isometrically embedded images of a plane, for instance. Okay, so why do you have this in the Weil-Petersen metric? Well, I have to be careful with this because there's some cases where it is Gromov hyperbolic. Okay, but if the complexity, and I don't remember what the count is. The complexity is greater than 3 or something like that. Okay, and what's the obstruction? Well, if you have a product metric, so then I can take a geodesic in here. On this side of the product metric, I can take a geodesic in here. And then the product of these two is also geodesic. Okay, so this immediately gives you a copy of R2.
So it's near the boundary Teichmüller space with the product.
Sorry?
So it's near the boundary where you have product in the car.
Exactly, yes. Yeah, but I mean, this one is quasi-isometric to the, you get exact products on the boundary. Yeah, you get exact products on the boundary. So you get quasi-products in here. Okay, so I have about 3 minutes remaining, and not even. So what I want to say is sort of what I'm going to look at tomorrow. Okay, so part 2, which is of the lectures, is going to be to look at the geometry of the Pants graph. Okay, look more into the geometry of the Pants graph. And I'm just going to look at the Pants graph as if it was the only thing in the world that I cared about. Okay, and I'm going to forget about the Teichmüller space. And in particular, you can ask this type of question. So here's a question for you. Okay, which is just motivated by what I just did. Like it's not at all a consequence of what I just did. So take P and Q belonging to the Pants graph, okay, such that P intersection Q contains a curve. What I mean is this curve is both a part of P and both a part of Q as sets. Then does there exist a geodesic? I'm taking geodesics in here. Between P and Q. Pants decompositions. With alpha. So I have two Pants decompositions. They both have a curve in common. can I find a geodesic in the Pants graph between these two Pants decompositions that always contains this alpha? Okay, this is exactly what happens in Teichmüller space with a Ray-Peter symmetry. If I have two surfaces which are pinched down to the same curve, any geodesic between them is going to have this curve pinched down to 0 all the time. This is exactly the convexity of stratum. Here I have a similar notion of stratum, which are parameterized by curves. And I'm asking you whether or not, if this curve lies in a Pants decomposition, whether or not I can always get in a geodesic from any pair of Pants that, any Pants decomposition with this curve to any other with this curve that always retains this. And to up the stake, I'll offer a bottle of Chateau Picos. There we go. Thank you very much.
Question? So I think the causal isometry is reasonable, right? If you have two.
Not only is it reasonable, it's true.
Oh, true. Okay.
So that's it.
Okay. So true. So Pants complex was first introduced by Thurston and Hatcher, right? Is that right?
The Pants complex?
Yes.
Well, almost.
Oh, almost. Okay.
I mean, the Hatcher-Thurston complex is almost the Pants complex.
I see. Okay. So what's an application of Pants complex? So you tell us more.
What's the application of the Pants complex?
Yeah, here's one.
Well, I mean, this is, well, my point is that now I'm only studying the Pants complex for the sake of the Pants complex. But if you want an application of the Pants complex, for instance, you can compute the diameter of moduli space with the Ray-Peter symmetry.
I see.
That's an application. Yeah?
Can you find for some G is the center of moduli space, that point or those points which are biggest distance from the boundary?
That's a very good question.
I don't know.
I mean,
Some G's there are no such a thing.
in fact, it's not even clear whether or not that's well defined.
It's finite state, I think. Like kind of convexity.
No, but you want, sorry, you want the center of moduli space,
The
right?
maximum distance to the boundary.
Yeah?
So it would be a disk, it would be the center.
I don't know, okay, I mean, I understand that they exist. The question is more whether or not it's unique, whether or not there's a finite number of such points, whether or not that type of thing.
What's the
It's
question
not clear.
again? Sorry.
Norbert is asking whether or not there's a point in Teichmüller space, right?
Yes.
No, in moduli space.
In moduli space, okay.
Yeah.
Sorry, in moduli space, that is maximum distance away from all these boundary points. Okay, so,
Oh, I see.
okay, so, it's clear that such points exist just by capacity arguments.
Yeah.
The question is whether or not, it's not known whether or not there's only a finite number of points that have this, for instance.
So in some sense there must be terribly symmetric.
Not if there's not a finite number, not if you get a whole,
Yeah.
okay, then they're not symmetric at all. But I mean, you'd expect exactly to be these, and you'd expect these points to be
Defined over Q bar.
extraordinary, right?
Defined over Q bar.
Okay, but defined over Q bar is not extraordinary in modular space.
No, but then you have a picture, and then we learn we have something to look at.
Yeah, but I mean, the defined over Q bar is dense, so that's not so exceptional. So you'd really expect that it has some extraordinary properties, much more extraordinary than defined over Q bar.
Ever a rational number is exceptional, in my opinion.
So how about
these are all very good questions.
So how about in the case when the homogeneous is equal to 1?
Yeah.
Right? When the modular space is a modular curve.
Yes.
So what is the point with the maximum distance?
I don't know.
Okay. No more question. I think we can have a tea break. Yeah. Thank you. So that's your result about estimate in the diameter.
Yeah.
You make use of Pants.
Yeah, exactly.
Pants number 30. Okay. Yeah, that's good application.
Yeah.